Good afternoon, everybody. I'm going to be aiming the next 20 minutes at those who have little or no computer science background. I've just been using OR, and it's my first foray into programming as well, using OR for the last 7 months or so, so forgive me for any repetition for others who have knowledge of other computer programs. So I'm just going to initially spend the first couple of minutes going through some of the basics in OR, the data requirements, some useful tips, and the error messages. I'll spend most of the talk showing you some data clustering examples and a regression analysis example. With the data requirements, the data is processed as vectors, so you have to have the same data type in each column. If you mix numerics and text strings, it will import everything in as a character and you won't be able to process your data. It's advisable when you're doing your analysis or coding to set up each a set of analysis as a project, and then it'll keep all the file paths. And don't save your workspace at the end of each session. You're better off to save your history, and then you're starting each time the new slate. Some of the tips that are worth remembering, but obvious to some people, but not to if you haven't used OR before. OR is cap sensitive. The indexing in OR starts at 1, not 0. It's also very important, I have found, to start out when you're doing any project with data collection or anything, start out with your data nomenclature as consistently as possible. I'll talk about that a little bit later. And then also always worth remembering about the use of the different brackets. So the round brackets are for commands. So you'd have a command and then the information for the command inside the round brackets. Square brackets are accessors, so you have your data set or your matrix inside the square bracket, and then the curly brackets are for the functions. The other thing in OR that OR can be tricky with is date formatting, and it's worth going through a couple of steps when you're trying to import dates into OR so that it reads them properly as a time series. So I'm just going through the data nomenclature issue that I was talking about. So I have a data set here with some rainfall, effective rainfall, and the data ID and dates. Taking in packages, tidyOR and Dippler, you get a number of packages to download with the base OR, and you can install any other ones directly off the internet if you need them. So reading in the CSV, just deleting some unnecessary columns, and then you get the string. Sorry. And so you can see here we have 4 numbers, 3 letters, and another 4 numbers followed by the month and the year. Or you could have the day, month, and year, but for this case it's the month and the year. So a monthly effective rainfall. And the data set has almost 4,000 observations, so you might want to take a subset and analyze it based on perhaps location or something. So perhaps we might want all of the NEWs. See that they changed down through the data set. All of the NEWs for the month of July. What you would normally do for this is you would use the separate substring or string split commands, and then subset or filter the data and analyze that subgroup of data. So what I'm going to do now is split that unique identifier for the data up into the OR ID and then separate out the date. And then you can see here we have borehole and we have the month, and it's fine for the first few, but then when the length of the identifier changed, we have months 22, 32, which are in fact the month 02, and then 2000, the year 2011, whatever. Now there are ways around this, obviously, but it will greatly lengthen your script writing if the unique identifier ends up being inconsistent. So just much easier to try and keep it the same from the outset. And then so with errors, you'll get lots of errors when you're starting out in OR. So check all the above, that you have your capitals, that you're accessing the brackets and using the brackets correctly, and checking for spellings. And then after that, you can copy and Google the error, paste it into your Google search bar, and you'll often get an answer up in GitHub or Stack Overflow, which is quite useful. The other thing to remember is when you come up with these error searches and you might find an answer to your query, it's helpful, I think, to copy and run the script in your own OR Studio rather than running it online, and you can see step by step what's actually going on and understand why your functions and your script isn't working. OR has many different clustering methods. The three main ones, or popular ones, would be hierarchical clustering, partition clustering, and model-based clustering. I'm going to talk just about hierarchical and partition clustering, and in both of these, the user chooses the number of clusters within the script based on the graphics that you get out of OR. The advantage of model-based clustering is that it uses a formal modeling method to statistically give you the number of clusters based on the distribution. Distribution with significance on the values within your data set. Each of the clustering methods you can use, within each of the clustering methods, you can use different mathematical methods, most common one being Euclidean. And I would start my clustering with a dendrogram because it's easy to see the visualization of the clusters. So I'm setting my file path, and I'm going to import in some data with annual ground water level range, and then take in the libraries for the packages I need, or we'll have a number of packages when you download it, and there are several more that you can get off the internet if they're not part of the original download. So the function we're going to use is hclust, and that's a hierarchical clustering method which uses the dissimilarity between variables based on Euclidean distance. And then when you plot, you get a dendrogram like this. And so here's the dendrogram, just put onto PowerPoint, and you can see approximately 3 clusters, or you could decide you want to pick these 2 as individual clusters, but in this case we'll take 1 cluster here, 1 here, and 1 here, and then to identify those within OR, we'd have to cut the dendrogram off here about 5. So that uses the rect hclust function. And then we can get a table of the output of the different variables in each of the 3 clusters. Another way of visualizing your data is to use CorePlot, which is a really nice visualization package for clustering, but you have to know how many clusters you have for that. So the way CorePlot works is you have to calculate a correlation matrix first using, so I'm just setting up a matrix here with the annual range values only and nothing else. And then you use the core function to get a correlation matrix. And then you get your core plot, which looks like this. It's quite a nice visualization. The core plot's very malleable. You can also plot the correlation index here, and you can set significance levels as well, as I'll show you. So here you can see the core plot where we've used the correlation index instead of the circles in the graphics. It's quite nice. showing the correlation from 0 to 1, obviously being full correlation. You can also put in the significance levels here. So I've put in a significance of 5%. So we can be 95% sure that these boreholes will correlate 95% of the time. And then the second method of clustering that I'm going to look at is the partition clustering. So the most popular one would be probably PAM clustering. And so we take in the library factor extra for that. I have to read in my data set again because I don't want it as a matrix like I had for the correlation. So PAM clustering uses the actual data points as the center of the clusters for calculating the maximum distance rather than the average value of a cluster, which means that it's less susceptible to outliers. And you can get a summary of your data as well. Like you could also do summary H cluster and see what data points fall into which cluster. And when you plot just in the basic core, you get a plot like this of your 3, because I've set the K value here to be 3 for 3 clusters based on the dendrogram. You get 3 different clusters. There's a nicer way of visualizing in PAM using this, or you'll also get, another output you get with the PAM clustering function is the silhouette plot, which shows the degree of correlation within each of the clusters. Obviously, the closer to 1, the higher degree of correlation. You can get a nicer visualization of the cluster plots with this fviz cluster function. So I'm just ignoring the actual data itself because a lot of work has to be done in this data set, but you can just see it's a nicer output, a bit like the ggplot. A logical follow-on to cluster analysis would be to undertake a forecasting model, such as regression analysis. Prior to undertaking your regression analysis, you'll have done a lot of data cleaning and normalizing. And this plus the regression analysis is an iterative process, which would be much speeded up by using OR. It's an idea also to just check for association at an early stage between your numerical variables using Pearson, or if it's ranked variables using Spearman. And then I'll just go through the code for a simple regression, multivariate regression, and then some regression validation. And I'm first going to do the Pearson correlation just to check the extent of the relationship between the numerical variables, which is my x value of effective rainfall and the log of the effective rainfall, and the y value, the log of the range. And we get a correlation, a Pearson correlation 0.25, and I'm doing it again with the cube root of the x value because that came out well when I was normalizing the data, and we get 0.26, and so the output also gives you your t-value, degrees of freedom, and your nice slope p-value and confidence intervals. Take the packages in, ggplot package and grid for the regression model. The code for the model is just LM for a linear model, and we're plotting the y value against the x value and getting the summary output, which gives you your balance around the residuals. So we want your balance to be pretty good, close to 0 between the two of them. And then you get your intercept and your coefficient with x, your standard area, t-values, p-values for each of these, and the overall p-value for the model, and our r squared. And then if you want to call up the coefficients, so you can put them in an equation on your plot later on, you can just call it up with the command coefficients. And then we can do the plot, add the line with ab line, AB line. And then this is just a line equation using the coefficients, so we can put that on later. And so this is the plot that you get with just RStudio. And we can use ggplot to get a nicer graphic output, and choice of lots of colors, and adding the line that we'll do there. What you can also do then is separate out some of your nominal variable within your data using the same model. We're grouping it separately by adding different colors to the data points on the plot. And so I'll bring that up on PowerPoint, and you can see we get a number of different fit lines for the different groups for the nominal variable within your model. And then if we want to do a multivariate model, just bringing in the package ggfortify, which gives nicer graphics for multivariate models. It's the same, obviously, LM, you just add in all your other variables, and you'll see how they come out then in the summary. You get a coefficient for each variable, the intercept and the coefficient for each variable, and you can then see if some of the variables are significantly correlated or not, and you get your R squared bottom. These are just plotting commands. And so the output that you get with a new multivariate model isn't just like a plotted XY. It just gives you the model diagnostics. And so this is the diagnostic plot output you get for a multivariate model. You can check the balance of your residuals, normality of your data on the QQ plot, reliability of the model in different areas of your data where the data is sparse, less reliable, and then the outliers, or if there's any outliers. So then when you've gone through the iterative process and you're happy with the final model, you can then plot your Y variable against your predicted values and against your residuals as a check. In the absence of a validation set to run on your model, you can do an internal cross-validation on the model using this CVLM function. So that divides the data into a smaller training data set to run the model on, and a larger data set to validate it on, and it keeps doing that in iterative loops throughout the data. You can tell it how many times you want to divide the data into these groups by allocating the number of folds. And the packages it needs for that are lattice and DAG. And so you get something like this for the cross-validation plot. And then here we have the plot of the variables against the predicted and the residuals, which are all of these hopefully get to one way of validating your model. So that's everything. And I hope everybody got something out of this talk, and I welcome any questions. Thank you.